All right, good morning, chemists. Let's get started here. So we're on electrochemistry, chapter 20. This is the last chapter for midterm 3. I will be having a midterm review session on Monday. It's not next week, but the following week. I haven't made the packet yet, but I will hopefully tomorrow and send out that information here soon. And my plan is also to write at least one paper practice midterm so I can post that information by this weekend. So, you can kind of start your preparations for midterm 3. So just a reminder, I will post a total of 2 practice exams by next week, and then the department provides 3 more. So that is 5 practice exams for you, plus the Zoom packet, plus your recitation packets, tons of practice problems for you for midterm 3. Reminder, what is on midterm 3, it's the second half of chapter 17, so that covers titrations. It covers KSP, so solubility product, we like that one, and KF, so complex ion formation. So that's chapter 17. Chapter 19 was chemical thermodynamics, where we studied entropy, delta S, and Gibbs free energy, delta G, and that chapter explained why we see chemical reactions happen at all. And now chapter 20 is electrochemistry. And what you'll see here soon is that a lot of these concepts are all interrelated to one another. Why a redox reaction happens is because the cell potential, when you put the cell together in the correct order or in the correct direction, we get a positive cell potential. A positive cell potential gives us a negative delta G Gibbs free energy. And so if we recall from chapter 19, when delta G is negative, the reaction is spontaneous in the forward direction. Versus if you have a positive delta G, the reaction as written is non-spontaneous, but if we were to reverse the reaction, because delta G is a state function, if we reverse the reaction, we change the sign of delta G, the reverse reaction is spontaneous. And so cell potential E is related to delta G, and it is also related to K as well. And so if the forward reaction is really, really spontaneous, you make a lot of products, K is large. If K is large, then your delta G is negative. All of these things are related to one another. And so hopefully by the end of this chapter, all of it will come together. All right, so chapter 20. So we started the beginning here where we I wanted to give us a template here and help you recognize that this chapter, electrochemistry, is actually very much related to some things that we learned in 1210, specifically single displacement reactions, redox reactions, and using the activity series. Basically, when using the activity series to predict if this reaction happens or not, if we mix copper solid and silver nitrate, does this reaction happen? It in fact does, because the metal, where's copper? Copper is higher on the activity series than the ion that it's reacting with. So it's reacting with silver. So if we look there, silver plus, the ion is lower on the activity series. If we were to swap them, so if we were trying to react copper 2 plus and silver solid, no reaction would happen. And the question is, well, why? Back in 1210, you just believed me that the metal has to be higher on the activity series than the ion, but it's all because of delta G. In one direction, delta G is negative. In the other direction, delta G is positive. And it's related to cell potential. So we reviewed some of these things, net ionic equations, so we can better see what's going on here. We know that these nitrates are spectator ions, so we can essentially ignore them. They're not reacting. So we know that this reaction is between copper solid and silver plus aqueous, and that's what we focus on. And we see that the products we make are silver solid and copper 2 plus when we take away those nitrate spectator ions. And that's what we're focusing on, because if you track the charge of copper, we see it's going from copper solid to copper 2 plus. versus silver is going from silver plus to silver 0. So we see that there's this transfer of electrons. And so the definition with, keeping track of where electrons are going, we say that copper is being oxidized because its oxidation number is going up, going from 0 to 2+, while silver is being reduced because its oxidation number is going down. And so that's some review from 1210 oxidation numbers to help you identify what's being oxidized and reduced. And we can also assign oxidizing agent and reducing agent. With those definitions, it's essentially backwards. So whatever is being oxidized is called the reducing agent because that is what's giving up the electrons to reduce the other species. So in this case, because copper is being oxidized, copper solid is the reducing agent, and then silver plus, because it's being reduced, is the oxidizing agent. So that is all review. All right, so there's that. And so some of the new ideas here is now we're actually going to keep track of electrons and see their significance in some equations. Can we look at this, balanced redox reaction? Can you tell me how many electrons are being transferred during this reaction? How many electrons? So if you take a look at the charges, it'll help you. So you see copper is going from 0 to 2+. So how many electrons are involved in that process? 2, yes. And so at the last class, someone asked me, okay, yeah, I see that copper is losing 2 electrons, but what about silver? So here's the beauty. As copper loses 2 electrons, those 2 electrons have to go somewhere. Where are they going to go? They're going to go to silver. So if you look at silver, silver is going to gain those 2 electrons. So you might be thinking, well, it looks like it's only gaining 1 electron. It's going from silver plus to silver 0, but look at the balanced chemical reaction. How many silvers are reacting? 2 of them. So 2 silver pluses are gaining 2 electrons to make 2 silver 0s. So that's this next step here. We're actually going to balance redox reactions, and it's all about balancing the electrons in addition to balancing the actual atoms themselves. All right. So there's that. There's oxidation numbers we went over. Basically, if you think charge of the atoms, it'll get you halfway there. We assigned some oxidation numbers. We predicted redox reactions. And again, this rule from 1210 helps us predict, based upon the activity series, whether a reaction occurs or not. But now in this chapter, we're actually going to calculate cell potential. And when cell potential is set up in such a way where it's positive, a spontaneous redox reaction occurs. So we're kind of expanding on this idea, but it's still the same exact thing. You can calculate the cell potential produced by any one of these reactions using our standard reduction table, which I'll introduce in a little bit. Okay, so we answered this question, with silver and copper. All right, we said that 2 electrons are being transferred, yes, and so here's our standard reduction potential. All of these half reactions, though in this way, they're written in the oxidation form, so they're all written as like the solid becoming the ion and releasing those electrons. In this chapter, we're going to look at standard reduction potentials. So these are all written as reduction half reactions, where silver plus is gaining an electron to make silver solid. So there's a small little difference here. See how silver is at the top of this table, but kind of at the bottom of this table? That's because we've flipped the reaction for our standard reduction potential. So you see the voltage that's produced for all of these half reactions. And I'll comment and explain how we use these half reactions to calculate spontaneous cells. All right. Okay, so let's do some more balancing because that is a large learning objective for this chapter. I can promise you for a fact you will at least have to balance one redox reaction on the exam, at least one, maybe even more. It might be part of a question, balancing redox reactions. So we tracked what was being oxidized, what was being reduced in this reaction, where usually I start with just getting the oxidation numbers to decide what's being oxidized and reduced. And so we answered all these things. In this example as well, 2 electrons are being transferred because zinc, it looks like it's losing 2 electrons. as it's being oxidized, and those 2 electrons are being gained by those 2 H+ cations to make a neutral H2. So we see that the electrons lost in one half reaction is gained somewhere else, and that N value, the number of electrons, stays the same here. All right, so we balanced that one on Tuesday. So the big idea here with balancing redox reactions is, closely similar to how we balanced reactions in 1210, where we just take care of atoms, making sure that the number of atoms of each element are the same on each side. But the thing here in redox reactions is electrons are also being transferred as well. So in addition to balancing those atoms, we need to balance the number of electrons too. We need to make sure that electrons that are being lost in one half reaction is being gained in another half reaction. So this adds a layer of complexity to balancing redox reactions specifically. We never had to worry about it for previous reactions that we did earlier. So I have a strategy up here that if you follow, I think it's, how many steps is it? 7. 7 steps. If you follow the 7 steps, you'll always be right. All right, so we just balanced this one, zinc reacting with acid, H+. That one's kind of easy to balance because the reason is if you balance the atoms themselves, all right, if I balance, so that's all I need, just 2 H+ to make the atoms balanced. It just so happens that the electrons are balanced too. So that reaction's balanced, and it's an easy one. Where it gets harder is where we have lots of different complex substances being oxidized and reduced. This is where we actually have to use the strategy. So this one's a lot harder, all right? Me personally, I can't just look at that reaction, the second one, and be like, oh yeah, those are the coefficients. It's a lot more complex. So we have to follow the 7 steps on the next slide. All right, so here's the strategy to balance a redox reaction, and the way we do it is we call it in acidic conditions, and you'll see why. So this is the strategy, all right? First, you want to label all of your oxidation numbers of your atoms to figure out what's being oxidized and what's being reduced. This method is called, I think it's called the half reaction method. And you'll see why. It's because we separate the reactions via their half reactions. So once you've identified oxidation numbers of everything, you want to split those half, you want to identify what's being oxidized, what's being reduced, and build 2 different half reactions. So identify, separate those 2 half reactions. So you want to identify your oxidation numbers, basically, right? So once you started with 1 reaction, now you have 2 reactions. And so for each of those reactions, you now want to balance them in terms of their atoms. So to do that, first balance any of the elements that are not oxygen or hydrogen. All right, then you want to balance the oxygens by adding water to the opposite side. Water is H2O. All right, so if you have an uneven number of oxygens on each side, start adding waters to make the O's match. Once you have balanced the elements and the oxygens, now you want to balance the hydrogens. Okay, and so to balance the hydrogens, what you're going to do is add H+ to the opposite side. This is why we call it using the half reaction in acidic conditions. We're adding acid in order to balance the hydrogens. So that's why we say in acidic conditions. All right, so at this point, once you're at step 4, you should have all of your atoms and elements balanced. All of the elements, all of the oxygens, all of the hydrogens, those should be balanced. But now, because we're talking about redox reactions, we need to balance charge as well. So this is kind of the hard part. You want to balance the charges on each half reaction by adding electrons to the appropriate side. So the charges on both sides of each half reaction are balanced, right? And so this is where you can spot check yourself to see if you've messed up or not. Because we have 2 half reactions, one of them's reduction, one of them's oxidation, you should always have electrons on the appropriate side based upon what reaction that is. So in your reduction reaction, your electron should be on the reactant side, wherever you put to balance it. On your oxidation reaction, your electron should be a product because your substance is losing electrons. I know I'm just talking a lot. We'll do an example here soon. So Once you've balanced the charges, now everything's balanced. Atoms, elements, and electrons. Once you're at that point, you can combine those two reactions, but you want to make sure that the number of electrons transferred in one half reaction matches the other. So you might need to multiply, one or both of the reactions by some coefficient to make sure that the number of electrons that transfer match each other. All right, and then at that point, electrons should cancel on opposite sides, and if you have extra waters hanging around, you'll want to cancel those as well. All right, I know that was a lot, so let's do an example. All right, so those are what I call the 7 steps. I think the book has less steps. They have, less steps. So let's balance this under acidic conditions. All right, so we had cadmium solid reacting with nickel 4 oxide to give cadmium hydroxide and nickel hydroxide. So I already did the first half step for you, and that's just getting oxidation numbers of our atoms. So they're under the atoms themselves. So this is how I like to go about this. I assign the oxidation numbers. I track to see, okay, cadmium 0 is becoming cadmium 2+. So cadmium is being what? Oxidized. Yeah, so I'm going to write my oxidation half reaction where I take that cadmium species, so cadmium solid, arrow becomes cadmium hydroxide. So that's my oxidation reaction, half reaction. And it's not balanced yet. That's okay. We'll go through all the steps. All right, and now I want to focus on the other thing. So the other thing is nickel. Nickel is going from 4+ to 2+. So nickel is being reduced. So we are going to write that half reaction as well. So you want to write out the whole species. So in this case, it's nickel O2 solid becoming nickel hydroxide. And if you, take a closer look here, you might look at oxygen and think, oh, is oxygen changing? If you look closely here, the oxidation number of oxygen is not changing at all, so we're not worrying about that. That oxygen is involved in the redox reaction, it's just not gaining or losing electrons. We're focusing on cadmium and nickel here. All right, so those are our two half reactions. They are not balanced. So we need to balance each of them separately. And so what step are we on? Balance other atoms first. So let's look at the cadmium one first, and we'll do it to completion. Are the cadmiums balanced? Yes, they are. If they were not, let's say if this was like CD2 or something like that, like there's a subscript 2 there, you would put a 2 coefficient in front of it. That's if you had to balance it. Next, you balance the oxygens in one of the half reactions. So if we look closely here, and I always like to give myself enough room. I probably didn't give myself enough room. There's 2 oxygens on the product side. So where do I want to put the waters? On the products or reactant side? Reactants. And how many? 2 of them. Yep, 2 waters. All right, so now the oxygens are balanced. Now we take care of hydrogen. So do make sure, if you look closely here, hydrogen shows up on both sides. So I always like to take inventory. I see on the product side, there are 2 hydrogens. And on the reactant side, there are 4 hydrogens. So where do I want to put the acid, the H+, on the products or the reactant side? To make the hydrogens match. On the product side, yes. How many? 2. Okay, now the oxygens and hydrogens are balanced. Great. All right, so you can, at this point, you can just check if it's a balanced reaction. 1 cadmium, 4 hydrogens. So remember, there's 2 hydrogens that we added from the acid, but that cadmium hydroxide also has 2 hydrogens on it, so that's a total of 4. Right, and then there's 2 oxygens on each side. Perfect. So the atoms are balanced. Next, we have to balance the electrons. So this is, again, where I kind of take inventory of everything. I look at all of the species on the reactant side and ask myself, what's the total charge there? So to me, there's a total 0 charge on the reactant side, but what's the total charge on the product side? +2. Yes, because that acid that we added is a +1 each of them. All right, so the total charge on the product side is +2. All right, so the charges aren't balanced, so the only thing we can do is add electrons. Remember, electrons are what charge? Negative. So wherever we're adding electrons, we're adding negative charge. So where are we going to put the electrons? On the products or the reactant side? Products. And how many are we going to add? 2. If we add 2 electrons to the product side, that brings that +2 charge to 0. And now both sides are charged 0. Okay, so now that half reaction is balanced. Good. So you can check yourself. Are the atoms balanced? Are the electrons balanced? And they are, in fact, all balanced. Okay, now we have to do the same thing for the other half reaction. Oh, this is where I like to check myself. Oxidation means what? Gain or loss of electrons? Loss. Based upon where we put those electrons, does that fit in oxidation? Yes, because an electron is on the product side. If you get to the point where you're placing electrons and you put them on the wrong side and it doesn't match, what is it, Leo goes Gur or whatever like that. So loss of electrons is oxidation, gain of electrons is reduction, yeah, that. If it doesn't match that, then you screwed up. You got to start over again. You probably either added H+ in the wrong place or something like that. All right, it will always match. Okay, so let's do the reduction one. Okay, so is nickel balanced? Yes. Is oxygen balanced? Yes, it is. So last thing we have to balance is hydrogen. So I see that there are 2 hydrogens on the product side. So I'm going to add acid. Where am I going to put acid? The reactants, yes. So plus how many? 2. Cool. All right, so now the atoms are balanced. Now we add electrons. So again, I like to just take inventory of all of the charges on both sides and make sure, add electrons to make them match. So on the product side, there is a total of a +2 charge. On the products, there is a 0 charge. So where am I going to put electrons? On the reactant side. And how many? 2. So 2 electrons. All right. Yeah, always try to give yourself enough room on these half reactions. I never do. All right, so there we go. There are 2 balanced half reactions. All right, so that brings us to, yeah, the last step here, at least in this little thing from the book. We have balanced the electrons. Now to get back to our original balanced whole reaction, we just add up these two half reactions, but make sure that the number of electrons match one another. So look here, in our oxidation reaction, we lose 2 electrons. In our reduction reaction, we gain 2 electrons. So we can actually just add these 2 reactions as is. That the oxidation reaction loses 2 electrons, the reduction reaction gains those 2 electrons. If they didn't match, let's just pretend we had to add 3 electrons to our reduction reaction. How could we make those the transfer electrons match? We would multiply each of the half reactions by some certain coefficient to make them match. So we would multiply the ox reaction by 3, all the coefficients by 3. The reduction reaction, we would multiply all of them by 2. So it would be a transfer of 6 electrons before we add them up. But we don't have to do that here, so let me just erase that. All right, so in this one, we can just add them up as is. And what we'll see is that the number of electrons cancel one another. So let me rewrite this. Cadmium solid plus 2 waters plus 2 H pluses plus a nickel 4 oxide gives us a cadmium hydroxide plus 2 H pluses plus nickel hydroxide. And of course, because the electrons, they're on opposite sides here, they do cancel. But what else can other things cancel in this reaction as well? The H pluses, yeah, so we can cancel out those H pluses because they are on each side. So that is the balanced chemical reaction. So what is not obvious here, in the balanced version, we have waters present. See how there wasn't water in the original unbalanced reaction? So that's the difference here with redox reactions. Water is oftentimes present, or acid is oftentimes present in order for a redox reaction to occur. All right, so let's Let's answer these questions. What substance is oxidized? Cadmium. So you can just look back at these oxidation numbers and see cadmium increases, specifically cadmium solid. What substance is reduced? It would be the nickel 4 oxide solid. What is the oxidizing agent? It's whatever is reduced, so it's the nickel O2. What is the reducing agent? It's the thing that's oxidized, so it's cadmium solid. And then how many electrons are involved in this redox reaction? 2. The reason it's 2 is because we canceled 2 electrons on each side. So now it's kind of obvious, if you balance it correctly, the number of electrons that are being transferred. This one is a lot more complex than that zinc plus acid example. It's a little bit more complex. You might actually have to balance it to get there. All right, so that's balancing a reaction in acidic conditions. All right, so let's do another one. Okay, let's balance this under acidic conditions, but I didn't get the oxidation numbers for you, so I'm gonna do that. All right, so oxidation numbers. Hydrogen is usually +1. Sulfur has what oxidation number here? -2. Oxygen usually has a oxidation number of +2, so that means nitrogen here has to be +5 because there's 3 oxygens, so -6 has to give an overall charge of -1. So that's nitrogen. All right, sulfur on the product side has an oxidation number of 0, yay. And then nitrogen on the product has an oxidation number of +2 because oxygen is almost always -2. And so what you see here again is that oxygen's oxidation number isn't changing, so we can just ignore it. We want to look at the things that are in fact changing. So sulfur is being what? Oxidized. Nitrogen is being reduced. Awesome. So with those arrows I've drawn, those are the 2 half reactions I have to write. Right? So I always like to do oxidation first. So let's get that oxidation half reaction. I'm going to take the total substance that's oxidized, so H2S, arrow, S. And then my reduction reaction is NO3, arrow, NO. Great. So what do we have to do? We have to balance the atoms. So are the sulfurs balanced? Yes. So now we move on to oxygens. Are the oxygens balanced? Yes, because 0 is balanced with 0. Now, are the hydrogens balanced? No. What do we use to balance hydrogens? Acid. So where are we going to put H+? On the products. So we're going to put 2 of them there. And then the last thing we balance are electrons. Where are my electrons going to go? Products or reactants? Reactants? Remember, electrons are negatively charged. So don't skip this step. Just take inventory of your charges. The reactant side has an overall charge of 0. The product side has an overall charge of +2. So we actually want to put 2 electrons on the reactant side. And is that consistent with an oxidation reaction? Yes. Leo. Loss of electrons is oxidation. So then now we do the same thing for reduction. So do them one at a time. Are nitrogens balanced? Yes. Are oxygens balanced? No. So how many waters? 2. All right, so I screwed up the hydrogens, but that's okay because I can just add acid. All right, where my H+ is going to go? The reactants. How many? 4 of them. 4 H+. All right, and now it's the hardest part, the electrons, and I'll be the first to admit that electrons are harder to balance, so that's why I don't like to skip the step of just taking inventory of all of the charges as written. The total charge on the reactant side is a +4, and on the product side, the charge is 0. So where are my electrons going to go and how many? They're going to go on the reactant side. So did I mess something up? +3. Oh, yes. See, I told you the electrons are hard to do. I just looked at the H+. I forgot that nitrate itself has a charge. Very good. Yeah, it's +3. Okay, there you go. All right, so how many electrons do we add? +3, yes. Yeah, don't be like me. Don't skip that step of inventorying all of your charges. Okay. All right. And is that consistent with a reduction reaction? Yes. So if you split your half reactions, all right, and you balance everything, and both of your half reactions have electrons on the product side, then you messed up. Or if you do and both of your electrons are balanced on the reactant side, you messed up. And you got to go back. All right, so we have electrons being lost and gained somewhere else. Can we just add those two reactions as is? No, we need to make sure the electrons match. So I'm going to multiply that oxidation half reaction by 3, and then the bottom one, the reduction reaction, by 2. So I'm going to change all of the coefficients here. I'm just going to write what the new coefficients would be because I'm lazy. So H2S, there's a coefficient of a 3. There's 3 sulfurs. There's 6 H pluses, and there's 6 electrons. And then times 2 in the reduction reaction, there's 6 electrons, 8 H pluses, 2 nitrates, 2 NOs, and 4 waters. Because that will help me save a step when I add those 2 reactions up. So now I can just add them up. All right, and I see that I have 3 H2S's. Those 6 electrons cancel, so I don't really have to write them. Then I have 8 H pluses. I have 2 nitrates. I have 6 H pluses. I have 2 NOs, and I have 4 H2Os. Is that my final balanced reaction? No, I can do one last thing. I can cancel H pluses. All of them? No, only some of them. So see, I have 8 H pluses on the reactant side, 6 on the product side. So I can cancel all 6 of those H pluses, leaving 2 H pluses on the reactant side. That is our balanced chemical reaction. All right, so in this example, H plus is required to make this redox reaction go. Yeah? So the question is, when we're balancing electrons in half reactions, does it have to go to 0? No, it doesn't. No, it doesn't. They just need to match, and you want to make sure you add the minimum number of electrons on the appropriate side to make them match. I'm hoping the next example we do, it's different, or it's what you are asking. Yes. So just so it's just kind of a coincidence that both of these half reactions, when we added electrons, we made sure both sides are 0, a total 0 charge. It doesn't always have to be that way. We just have to add the minimum number of electrons to make them match. All right, so, okay, what substance is oxidized? So H2S, what substance is reduced? It's the other thing. What's the oxidizing agent? It's the nitrate. What's the reducing agent? It's whatever was oxidized, so H2S. How many electrons are involved in this redox reaction? It is 6 because of how we canceled it. And I don't know about you, all right, but when I looked at the unbalanced reaction, I couldn't tell right away that it was 6. I actually had to do the method of half reactions to get it, to figure out, okay, how do I get those electrons to cancel? Okay. All right, so that one was a little bit harder, so let's do an even harder one, and then I'll do a demo. All right, so this one's a little bit harder. Let's look. Okay, yeah, actually, one last thing. So remember what these coefficients mean. So we have this new balanced chemical equation. The stoichiometry comes from those coefficients. So these balanced redox reactions also follow stoichiometry that we know and love. So that's what this next question is. Let's look at a reaction between permanganate and oxalate. And I am asking how many moles of permanganate is required to fully oxidize oxalate. So this question is really asking, what's the balanced chemical reaction? What are the coefficients within there? So it requires us to balance the whole redox reaction. And then the follow-up question is, let's actually do the neutralization and figure out how many milliliters are required. All right, so there's really nothing new on this slide other than the new method of balancing redox reactions, which is quite hard because there's just a lot of places to screw up. All right, so that's why you got to practice. All right, So let's balance this. And I didn't give you charges or oxidation numbers because I'm mean. All right, so permanganate. Manganese has an oxidation number of +7 because oxygens are -2. Oxygen in oxalate is -2. So what's the oxidation number of one of those carbons? +3. Because there's 2 carbons, so +3 becomes +6. There's 4 oxygens, so a total of -8. 6 minus 8 equals -2. Okay, great. Manganese on the product side has an oxidation number of 2. That one's easy. Carbon has an oxidation number of 4 in CO2. And then oxygen is -2. And you see, again, oxygen's not changing, so we can just ignore that. We care about the things that are changing. So manganese is being what? Reduced. And then carbon is being oxidized. Yay. Right. If you do these steps and you find that all numbers go down, then you screwed up and you should try again. Something needs to be reduced, something needs to be oxidized. All right, so now let's get our half reactions. Let's get our oxidation reaction first. So we write all of oxalate. C2O4, 2 minus, arrow, CO2. Then our reduction reaction. MnO4 minus, arrow, Mn2 plus. Great. All right, so let's do the oxidation one first. Okay, balance the atoms. Are the carbons balanced? No. So we're going to put a 2 coefficient in front of CO2 to make it balanced. All right, next we do oxygens. Are the oxygens balanced? Yes, they are. Good, so we don't have to add any water. Hurrah. Are the hydrogens balanced? Yes, because there are no hydrogens. Yay. So now we balance electrons. So where are we going to put the electrons? On the product side. Yeah, so in this example, if we take inventory of all of the charges, the reactant side is -2. The product side is 0. So in this case, we're not balancing to a net 0 charge on both sides. We're actually going to add 2 electrons on the product side, so both sides are -2. And that's okay. There you go, Dominic. Yeah. All right, so then the reduction reaction. Are manganese balanced? Yes, they are. So then we balance oxygens. So I'm going to add 4 waters on the product side. All right. Now I balance those hydrogens that I just added. So I'm going to add 8 electrons on the reactant side. No, not electrons, hydrogens, sorry. Hydrogens on the reactant side. So now this is tough. How many electrons do I need to add and where? 5, I think. Let me check. Okay, hydrogens +8 -1, so that's a +7. And then manganese is +2. And so if I add electrons, if I add 5 electrons to the reactant side, I can bring the reactant side down to +2 so it matches the product side. So I'm adding 5 electrons here. Agreed? Yes. Okay, cool. So now I have 2 balanced half reactions. Can I just add them up as is? No, I need to multiply by some coefficient. All right, so I think, what's the math term? The lowest common multiple. What's the lowest common multiple of 2 and 5? 10. Yeah, so I'm going to bring the number of electrons on both half reactions up to 10. So to do that, I'm going to multiply the oxidation reaction by 5 and then the reduction half reaction by 2. And so then the hard part here is combining both those half reactions and canceling out what you need. So I always like to rewrite the coefficients. So there's 5 oxalates, 10 CO2s, 10 electrons. The reduction reaction, I'm multiplying by 2, so 10 electrons, 16 hydrogens, 2 permanganates, 2 manganese, 8 waters. So if you're clever, you can try to cancel stuff out that you can before adding the 2 reactions up. But I do see that the number of electrons cancel, and I don't think anything else cancels because only the reduction half reaction has water and H+. So now we can just add them up as is. So the full balanced chemical reaction is 5C2O4, so that's our oxalate, plus permanganate, or sorry, 2 permanganates. Oops, don't forget the coefficients. 2 permanganates plus 8 H pluses. And remember, these electrons are canceling, so I'm not even going to bother writing them. Next, we have 10 CO2s, 2 manganese, 2 pluses, and 8 waters. There's our balanced chemical reaction. And so now we can finally answer the question, how many moles of permanganate do you need to neutralize oxalate? And so it's in the balanced chemical, in the chemical reaction. So basically it's just stoichiometry. For every 5 moles of oxalate, you need 2 moles of permanganate. And so it's no different than any stoichiometry you've done before. But in order to get the 5-to-2 ratio, you had to go through all the steps of balancing half reactions. Yes. Yeah. 16, yes. I just wrote the wrong thing. Thank you. I told you there's a lot of places to go wrong. Yes, it's 16. I wrote 16 up there. It's because I skipped a step, because I'm lazy. All right, so let's actually answer this question. How many milliliters of permanganate is required to neutralize 200 milliliters of sodium oxalate? This is a Chem 1210 question. If we gave you the balanced chemical equation already, it's just a Chem 1210 question using molarities and stoichiometry. But what makes this 1220 is I don't give you the balanced chemical equation. You have to do it yourself by the method of half reactions. So let's actually do this. We're going to start with 200 milliliters of that sodium oxalate. I can use molarity, so 1 liter, or I can say 1 milliliter is 0.10 millimoles of the oxalate, C2O4 2 minus. And then now I can use the stoichiometry up here that for every 5 moles of C2O4 2 minus, I need 2 moles of the permanganate. And then I can use the concentration of the permanganate that's given. So I'm going to put 0.1 millimoles of the permanganate on the bottom, and then 1 milliliter up top, right? So that's just 1210, right? But the difference here, I just didn't convert to liters. So I just kept everything in milliliters. So when you do this answer, when you use molarities and use stoichiometry, it just stays in milliliters. Because you learned how to do that. You learned how to do that already in chapter 17, right? So I started with volume, multiplied by molarity, used stoichiometry, and then divided by the molarity of the new thing. There's nothing new there. And so the answer here would be, we need 80 milliliters of our permanganate to completely neutralize oxalate. All right. Okay, so this is where I want to do my demo. Okay, so I got a demo up here, so let's zoom in. I'm going to basically do this reaction. I'm going to do the titration here because permanganate's really cool, and you see it in the picture. Permanganate is really purple, all right? It's purple, okay? Oxalate, I'm just going to say, is colorless. Manganese 2+ is also colorless. Actually, all of the products are colorless. Right? So what's cool here is how we know a redox reaction is happening is we take this purple substance, we mix it with this colorless substance, and everything becomes colorless. So that's kind of indication that a redox reaction is happening. So the demo lab did not give me oxalate. They gave me a different substance that we will oxidize, but it's no different. Sodium nitrite. It doesn't matter. So here's my colorless oxalate compound. I'm just going to dissolve it and prove to you that it is colorless. Okay, it's all gross. Okay, I don't know how much to add. They said some. There we go. There's my oxalate. It's colorless. Do you agree that it's colorless? It is colorless, yes, very good. All right, and then this is potassium permanganate. So this should be a purple color. And these are our two reactants. See, I don't want to add them together right away because I want to control the redox reaction that's happening. All right, so this should be a very bright purple. I don't even have to add that much. There we go. Okay, I probably added too much. All right, so that is the potassium permanganate, the purple reactant. Okay, so what do you think will happen when the redox reaction occurs? I'll mix these two things and the products should all be colorless. So yeah, that's what we think will happen once the redox reaction happens. Okay, so let's pour that in there. Do I put all of it? Okay, I'll just put that much. It's fine. Okay, so. Is a redox reaction happening? Don't think too hard. Did a redox reaction happen? No, because what do you see? It's still pink. So that means we still have reactant present. Then why did I do it? Why did I do it if a redox reaction didn't happen? So I just showed you the unbalanced reaction. Let's zoom out. And what is the whole balanced chemical reaction here? It's not just between permanganate and oxalate. What else is required for this reaction to happen? Acid. So is it acidic in there? No, it's not. So that's what we mean by balance in acidic conditions. We actually need acid in order for this redox reaction to occur. I've actually never done this demo, okay? All right, so here's just some sulfuric acid that I'm gonna add. Hopefully it'll happen. Hopefully, oof, it off-gassed a little bit. Okay, the thing said some. It said some, so we'll see how much some is. Okay, go, 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 go. So you tell me, all right, does this redox reaction require acid to go? Yes, it does, and we proved it. Wow, that was really cool, actually. We proved it by the balanced half reaction that acid is in fact a reactant. It's required for it to go forward. Even though it's not being oxidized or reduced, it's still a reactant, so you still need it. Cool. Do you think when I poured the two things, it was gonna happen? Did you think it was gonna happen? I thought it was, but yeah, based on the balanced half reaction, you do in fact need H+. That's a pretty cool demo. All right, good. Okay. So that was in acidic conditions, all right? So the method of half reactions to balance in acidic conditions, you follow those steps, all right? Those 7 steps or whatever. We can also balance redox reactions in basic conditions as well. They actually have different cell potentials, but that doesn't matter here. So to balance a redox reaction in basic conditions, and this is important because a lot of the redox reactions in like batteries and stuff actually occur in basic conditions, like our alkaline batteries. So to balance a redox reaction in basic conditions, the easiest way to do it is just start with the balanced reaction in acidic conditions first. So do the 7 steps in acidic conditions first, and then to get this reaction into basic conditions, what we're going to do is just add base. We're going to essentially add OH minus to just neutralize that H plus. So what I'm going to do is if I add 16 OHs here, H plus OH is what? Water. So by adding 16 OHs, I turn this into 16 waters. But if I add 16 OHs on the reactant side, I also have to add 16 OHs on the product side as well. All right. And so at this point, this would be my new balanced reaction. 16 waters, 2 permanganates, 5 of that, 2, that, and that. Can I simplify this any further? There's some waters that I can cancel. So I can balance it even further by canceling those waters. So I can cancel out all of those 8 H2Os, and that becomes 8 over there. right? So the method here for balancing in basic conditions, just start with the acidic condition, 7 steps, and then add OH minus to neutralize any H plus that is in your balanced reaction. That's basically it. And that's the easiest way to do it. And so the full balanced reaction here would be 8 H2Os, because this all cancels. 8 H2Os, 2 permanganates, plus 5 oxalates gives us 2 manganeses plus 10 CO2s plus 16 hydroxides. So our balanced reaction is a little bit different, right? What's interesting here is that the stoichiometry between manganese and oxalate, it remains the same. We just now have hydroxide in the balanced equation instead of H+, right? Okay, so that's kind of one layer of complexity that we can add to balancing a reaction. We can ask it in acidic conditions or basic conditions. I'll say 90% of the time we're dealing with reactions in acidic conditions. All right, so that's balancing redox reactions. All right. Okay, so that's the first two, great. So now we will talk about making voltaic cells. So we're gonna be making batteries. We're making cells that have, can produce a voltage spontaneously when we set up the cell. And so this is essentially how batteries work. It's why this potato lights up this light bulb. The potato isn't what's giving the making the electricity here. It's actually the 2 screws or the 2 nails. One of them's made of zinc, the other one's made of iron. That's actually what's making the electrons to light the light bulb. But essentially both of these things, our potato light bulb and our battery, is essentially a electrochemical cell, specifically a voltaic cell. A voltaic cell is a cell that's, when it's built, produces a voltage. So a spontaneous cell. And that's what we're gonna look at now. All right, so let's construct a voltaic cell. And essentially what a voltaic cell is a balanced redox reaction where the cell potential is positive when we set it up. So let's look at this half reaction. This one's a pretty simple one because I think it's already balanced for us. But we should be able to identify the half reactions. What reaction is being oxidized, or what substance being oxidized? Zinc. So zinc solid is becoming zinc 2+. Where are those electrons going? Products, so 2 electrons. So this one's pretty straightforward. The reduction reaction is the other thing. So we have copper 2+. It is gaining those 2 electrons and it is making copper solid. And so those are our 2 half reactions. If we add them up and cancel the electrons, you should get the overall balanced reaction we started with. All right, so memorize this, okay? So we know that Leo goes Gur. Loss of electrons is oxidation. Oxidation also occurs at your anode. So you need to memorize that too. Just memorize it. And then reduction happens at your cathode. So if you identify your oxidation half reaction, if you identify your reduction half reaction, you know what reaction is happening at your anode and your cathode. So I just memorize N-ox red cat. That's how I memorize those 2 things. So anode, oxidation, red cat, reduction, cathode. All right, and so that's just the terminology that that we use in electrochemistry. All right, and so this is in fact a spontaneous cell. If this was Chem 1210, we would look at the 2 reactants, zinc solid and copper 2+, locate these on the activity series. So copper 2+ is right there. Zinc is, where is it? Where is it? Right there. So does that fit the criteria for a single displacement reaction? Yes. The metal is higher on the activity series than copper 2+. So this reaction does in fact go forward. But in this chapter, again, we'll prove why, and it's because of cell potentials. All right, so will this redox reaction occur spontaneously as written? Yes, because we just proved it with the activity series. All right, can you tell how many electrons are involved in this reaction? 2, yes, because you can see it in the half reactions that we wrote. All right. What substance is losing electrons at the anode? Zinc what? Zinc solid, yes. And then what substance is gaining electrons at the cathode? It would be copper 2+. Copper 2+ is gaining electrons. Let's be super specific here. Because if copper solid gained electrons, would you get the product you want? No, you would get something weird like copper 2-, and that doesn't exist. So do make sure you're pointing to the correct thing. All right, what direction do the electrons travel? If you look at the half reactions, it looks like, the anode is giving up electrons and the cathode is gaining electrons. So it looks like it's going from the anode to the cathode. And that's exactly what happens. All right, and so this is what the electrochemical cell will look like, where we have our anode is made out of zinc. That's what we said, oxidation at the anode. So we have a zinc metal rod sitting in a solution of zinc 2+, probably zinc chloride. And then on the other side, this is our cathode that is made of copper solid, and it's sitting in a vat of copper 2+. And then when we connect these two electrodes, the anode and the cathode, what we see is that electrons are leaving the anode, because you can clearly see that from the half reaction, and it's being gained by the cathode. So electrons are going from anode to cathode, or they're going left to right, as long as you always draw the cell in this manner, anode, like left to right, anode, cathode, it'll always go left to right. All right, so what metal is the anode? Zinc. You can see it in the picture, and you can tell from the half reaction. And then what metal is the cathode? It would be copper. And so we see here that we need literally a solid zinc rod and a metal copper rod. And we'll do the demo here in a little bit. All right, so that is a spontaneous voltaic cell. So a spontaneous reaction is happening right now. We can identify number of electrons involved, what's losing electron, what's gaining electrons, and the identity of the anode and cathode, the two electrodes, based upon how we defined our oxidation and reduction half reactions. Okay, so let's look at it a different way, right? Because this is a spontaneous reaction. The reaction does proceed left to right. Okay, if we mix zinc solid and copper 2+, we will make copper solid and zinc 2+. So remember, a chemical reaction is happening. This is the same setup, okay? So tell me, as the reaction proceeds forward, as electrons move left to right in this cute little battery that we made, how will the mass of zinc solid change? It will what? Decrease. Why? It's becoming the ion. Yeah, zinc solid is of reactions. Don't forget, a reaction's happening. Zinc solid is a reactant. Zinc 2+ is a product. We are going from reactants to products, so the zinc solid mass should decrease over time. What about copper? Increase, yeah, because we're making it. We're making it. So all of that copper 2+ that's sitting in the solution here, it's going to deposit itself onto that copper rod. Cool. All right, what about the copper 2+ concentration? How's that going to change over time? It's going to decrease, because the idea is, well, where does that copper solid mass come from? It comes from the solution that it's floating around in, right? That those copper 2+ ions are going to attach itself to that metal electrode. And then how does zinc 2+ concentration change over time? It decreased. No. Did I circle the wrong one? Okay, cool. Copper 2+ decreases, yes, because it's being consumed, and zinc 2+ will increase because it's being produced, all right? And so that's what happens when the electrons flow from left to right, to a point, right, where copper 2+, we say that it's going to decrease its concentration over time, to the point where the concentration of copper 2+ approaches 0. Right? So if we consume all of the copper 2+, the concentration goes to 0. At that point, what's going to happen? Will it be a voltaic cell anymore? No, because we've run out of reactant. At that point, your battery is dead. And that's why batteries die, because they run out of the reactants that are needed for the reaction to go forward. So this is kind of just proving that, reactions, these redox reactions will run out over time, right? And so some small ideas here about this cell. So here's our anode compartment, our cathode compartment. They are separated by this salt bridge. So this porous membrane that it doesn't allow electrons to flow through, but instead what it allows is anions and cations to flow through. And so what I mean is things like sodium plus and chloride minus. So our spectator ions will move across that porous barrier in order for the sides of the half reactions to stay charge balanced. So if you look here, it says anions will travel towards the anode and cations will travel towards the cathode. So anions such as chloride, cations such as sodium plus. These are our counter ions. So the question is, well, why does that happen? Anions travel towards the anode because in the anode compartment, you are converting zinc to zinc 2 plus. And because zinc 2 plus is being produced, you need to add chloride minus to make it all charge balanced, that we can't just keep accumulating positive charge. So anions will travel towards that side to counteract that charge imbalance. And the same idea for at the cathode. At the cathode, that copper reaction is happening. And so cations will move towards the cathode because you're consuming consuming copper 2 plus, and so you're basically removing positive charge from that compartment, and so sodium cations will move towards that direction in order to make up that loss of positive charge. So that's a small detail there. Right, and so these anions and cations moving, it's not zinc 2 plus and copper 2 plus that are moving, it's actually smaller spectator ions that are moving between those compartments. All right, so I want to show you a voltaic cell. It's pretty cool. All right, so, and it's this one. I have a copper solution, you can tell because it's blue. All right, so there's one of my compartments. So if it's copper, the outside compartment right here, what's copper? Is that reduction? Is that the reduction reaction? Yeah? Yeah. All right, so the outside compartment, that is our cathode. That's where reduction is going to take place. And then I have this little porous cup in here. That is my other compartment. That's my anode. That contains a solution of zinc and a zinc piece of metal in here. So there's my anode, there is my cathode. So I'm going to harness the energy that comes off of this redox reaction to push this little thing. All right, so I got my little alligator clips to set it up, and they're separated by a porous cup to allow, okay, I can't let them touch, to allow those counter ions to move. There we go. So there you go. So there's the electrochemical cell. So we make a potential when we set this up, when we put copper and zinc, those half reaction compartments, next to each other and give the electrons a way to escape and move from our anode to our cathode, we can harness those electrons to drive a process like spinning this little wheel thing. And it will go on for a very long time. I think they did it overnight once. It'll run for about 20 hours. Okay. All right, so I mentioned, so we produced a voltage here when we put those two half reactions next to one another and gave the electrons a route to go. We can produce a voltage. I have a voltmeter, multimeter here to measure it, but I want to discuss what that voltage means and how we can measure it. So in order to understand the potential that electrons can be transferred in a half reaction, we need to set a standard point. So if we set a reference point, we can determine basically how well a substance donates or receives electrons given a half reaction. So let's just define a reference point. That reference point will be the reduction of hydrogen or reduction of H plus to make H2 gas. So this is called the standard hydrogen electrode, or SHE. So this is a reference electrode that we just set as humans as 0.0 volts. We just define that the voltage that is produced from a standard hydrogen electrode is 0.0, and that allows us to reference every other half reaction to the standard hydrogen electrode. All right. So what is the standard hydrogen electrode? It is the reduction of acid to H+. So you can see that half reaction right here. I will note that in these half reaction, the standard reduction table, all of these are written in the reduction form. So you see we have a reactant, we have electrons, and we make the product. They're always written that way. So for our standard hydrogen electrode, we have 2 H pluses gaining 2 electrons to make 1 H2 gas. And so what this looks like, what this electrode looks like, it doesn't look quite like our electrodes up here. You know, I have copper 2 plus, it's like copper sulfate or something, and I have a copper solid electrode. So in this example, it's easy to make a electrode because one thing is a liquid, a solution, the other thing's a solid. But if you look at the standard hydrogen electrode, that half reaction, is there anything in that half reaction that I can clip an alligator clip to? Look, H plus and H2 gas. Is there anything there that I can clip an alligator clip to? No. All right, so standard hydrogen electrodes, they're harder to work with because you're producing a gas. I can't stick an alligator clip on a piece of, on a gas, so instead we have to take a piece of platinum wire in order to make this electrode. It's actually quite complex, where see this like little wire right in the middle? That is platinum to allow H plus and H2 gas to interact with one another for that process. So basically I'm just telling you that actually using a standard hydrogen electrode is really complicated and hard. So that's why we need this reference scale. Once we have all of these reduction potentials referenced to the standard hydrogen electrode, we never actually have to use the standard hydrogen electrode, right? So that's the idea here of what that 0 signifies. That was just us chemists, scientists just setting where that 0 point is. It's actually really hard to use it. Okay, so what does this table mean? All right, so in order to make a spontaneous voltaic cell, when the reduction or the overall cell potential of your anode and cathode is a positive number, that is a spontaneous voltaic cell. So how do we calculate our cell potential? Remember, 2 reactions are happening, a reduction reaction and an oxidation reaction. So we're going to add up those 2 numbers in a certain way. So by convention, we're going to take the reduction potential that's at your cathode, and we're going to subtract the reduction potential at your anode. So being able to identify what's your cathode, what's your anode, super important here, all right? So what reaction happens at your cathode? Whatever is being reduced. And then what happens at your anode? Whatever is being oxidized. So all of those steps we just did, we're going to continue using them. So once you identify what's being reduced and what's being oxidized, you find them on this table, and you take the positive number of your cathode and you subtract whatever number is happening at your anode. All right. So that's by convention. And so if that number that you calculate is a positive number, then you do in fact have a spontaneous voltaic cell. So how we read this table here, focus on that 0 point or hydrogen, standard hydrogen electrode. So what these numbers mean is that if we have a positive reduction potential, it means that all of these substances are more easily reduced than hydrogen. So all of these are positive values. So typically these substances will be your cathode, usually, because they are easily reduced when they're above hydrogen. Anything that is below hydrogen, see how these are all negative numbers? So all of these substances are not easily reduced. And so instead, we can say, oh, they are easily oxidized instead. Because what happens when you subtract a negative number? You get a more positive number. So these substances are more likely to be your anode. These substances are more readily oxidized. So if we take a positive number, positive half reaction as our cathode, and then subtract a negative number as our anode, we'll get an even bigger positive number. Those are good voltaic cells with really high cell potentials. All right. Okay. Yeah. So oxidation, anode, reduction, cathode. Okay, go to bed tonight and say that 100 times. Okay, great. All right, so what do these cells look like? So here, I have two experiments. So each experiment has two half reactions occurring. So we need to kind of identify what's happening. So using this information, let's see if we can't calculate the reduction potentials of copper, zinc, and hydrogen plus, all right? So here's the first experiment. It looks like I have zinc at my anode and I have hydrogen at my cathode. That's experiment 1. And what we want to focus on is the measured voltage. That's the cell. So this is your cell potential, E cell. And then in experiment 2, it looks like we have a different cell potential being measured. This is our new E cell. Okay, come on, E cell. But in this experiment, I have zinc in my anode and I have copper in my cathode, all right? So we want to calculate what are the cell potentials of all of these things given these two experiments. These are the only things we know. And so just remember this equation. All right, is there any of these substances, do we actually already know what the the reduction potential is? What's the definition of hydrogen? It's 0, yes. So the half reaction, the reduction reaction for hydrogen, so 2H plus 2 electrons gives me an H2. We define the reduction potential of this reaction as 0, yes. So we know that one. That one's for the H plus H2 half reaction. That's a definition. Can we use that piece of information to help us get more information out of experiment 1? Look at where hydrogen is in experiment 1. Where is it? It's the cathode. What's in our anode? Zinc. So we can use this reaction or this equation. All right. The cell potential that's being measured here is 0.76 volts equals the reduction potential at our cathode minus our cell potential or reduction potential at our anode. Which one do we know already? The cathode. No, yes, the cathode. Yeah, so it's anode, then cathode. So that means 0.76 volts equals 0 volts minus whatever cell potential is happening at our anode, because that is the zinc. Zinc is our anode here, anode. So that means what is our cell potential for, reduction potential of our anode? It would be negative. Zinc is that zinc half reaction, so zinc 2 plus gives us 2 electrons to give zinc solid. The reduction potential for that reaction should be negative 0.76 volts based upon that picture. And the reason is because we know hydrogen cell reduction potential is 0. According to the picture, hydrogen is the cathode. And so if we do cathode minus anode, this reduction potential of zinc has to be negative 0.76 volts. Yes. Okay. So now we just need to get, yes, good, there's the answer right there. All right. So then we can use that information to give us more information about experiment 2. So now we know the reduction potential for hydrogen. We know the reduction potential for zinc. So what is occurring in experiment 2? It looks like what substance is the anode? Zinc. What substance is the cathode? Copper. So E cell, the potential is 1.1 volts equals cathode minus anode. Which one of those do we already know? We just calculated zinc. So we know the anode. Or no, yes, we know the anode. That's the one we know. So if we solve for the reduction potential of the cathode, that will give us what the copper half reaction reduction potential is. So I think setting this up, it's 1.1 volts equals the reduction potential of copper 2+ minus the reduction potential at the anode. So what number am I going to put here in those parentheses? 0.76 or negative? It's negative 0.76 because we always put reduction values in this equation. So see how it's reduction for both? Even though oxidation happens at the anode, you still want to always put the reduction values straight off the table. All right, and so what we get here when you solve for that, you get that the reduction potential of copper is equal to, what's the answer? 0.34 volts. There we go. All right. Okay. So let's check it, because isn't that the little spinny thing? Isn't that a copper zinc half cell? So let's just check it. I have a nice little multimeter here, so I have to turn this off. I have to turn it off, yes, because I'm going to measure it. I want to measure the voltage. All right, so we have copper in one cell, one half reaction cell. That's the anode, or that's the cathode. And then at the anode, we have zinc. So I'm just going to plug this in and tell you, it's going to be hard to actually see what the voltage is, but I'll prove to you that the voltage here is, it says 1.092. 1.092. Is that really close to 1.1? Yes, it is. Yeah, so there we go. Okay. I'll plug it back in. We have a couple minutes left, so I'll just plug it back in. Because they have to just trash the solutions. And so let's, we'll just keep letting it run. All right, so there we go. Oh, and then this little question down here. So if we set up a third experiment where we wanted to make a voltaic cell, and it was made of copper and the standard hydrogen electrode, what electrode would copper be? Would it be the cathode or the anode? Remember, we have to make a voltaic cell. Voltaic cell means what sign of cell potential? Positive. So in what way, what's the only way out of these two substances, so copper and hydrogen, can we get a positive value? Copper needs to be what? The cathode or the anode? It has to be the cathode, yes, because remember this calculation we do, it's always cathode minus anode, and so if we do -0, which is coming from hydrogen, it will make this overall process positive. But if it was the other way, if I made hydrogen the cathode and copper the anode, then it would be a negative cell potential, and that would not be spontaneous. Okay, cathode, okay, that was my demo. All right, so let's talk about line notation. It's annoying to draw these. All right, but it's nice, right? Like it's nice. You can see, oh, okay, yeah, it always goes anode, then cathode. So you can clearly see, okay, this reaction should be oxidation. This one should be reduction when I draw the picture. But it's annoying to draw pictures on Word documents. So scientists use what's called line notation to signify the same thing. So here's the line notation of this same electrochemical cell, zinc, and copper half reactions. So how we deal with line notation is we still draw everything or write everything left to right. So we want to draw the anode compartment, then the cathode compartment. There's just small little details here. So we typically want to tell the user what is the solid electrode that you're clipping your alligator clip onto. So in this case, on the anode compartment, it's zinc solid. Then you want to tell what bath it's swimming in, and you want to separate it by a single phase boundary. So that's what that single line means. You want to put that between anything that's different phase. So because it's a solid going to aqueous, you want to put a single line. And so zinc 2+ is aqueous. We also typically want to say the concentration. So in this case, it's 1 molarity. So this is the entire anode compartment. Now we want to talk about the cathode compartment, but backwards. So we want to draw a double line, which is our salt bridge. So this is what's separating our cathode and our anode. And then you say all the same things. What bath your cathode is swimming in. So in this case, it's copper 2+. I want to say it's aqueous. I want to say it's concentration. And then I want to say what the alligator clip is holding on to. And so in this case, it's copper solid. All right, and so those are the tips right there on how to do that. So it always goes anode, cathode, and the stuff that's attached to it. So let's do this one. Let's do this one, all right? We have like a minute. I bet we can do it. So we just say all the things left to right. You want to start with where you're sticking your alligator clip. Where is my alligator clip sticking on in that picture? Magnesium solid, yes. And it's swimming in what? Mg2+, so a magnesium chloride solution. And we typically want to say the concentration. Let's just say it's 1 molarity. So that is our anode compartment. Now we do the same thing for the cathode compartment. So I'm going to put that double phase salt bridge thing here. And now I want to discuss what is happening in here. So this one's a little bit more tricky. We have H+, because it's a solution of HCl. Typically it's aqueous and 1 molarity, but we also have H2 swimming around in there. So I want to draw another phase boundary and say, oh, there's H2 gas. Now, where is my alligator clip connected to? Is it connected to H2 gas? No. What is it connected to? Platinum, yes, because that is actually a standard hydrogen electrode. So there we go. That is our line notation for that last picture. But what's nice is it clearly shows you what half reaction is happening at the anode and cathode. It always goes anode oxidation, cathode reduction, left to right. All right, have a good weekend, everyone. Oh, remember, chapter 19 homework is due on Monday.